why don't we start with some basics and fundamentals so that we're all on the same page? And I know that most of you probably know all of this stuff. So programming is all about solving problems involving computers. This is kind of the cycle of how the problem solving continues on and on, as humans don't really ever run out of problems to solve. The very first step is the problem needs to be first found, but most importantly understood. It is next to impossible to try to solve something if we don't understand what it is we're trying to solve. The next step is the human actually solves the problem with an algorithm, writes an algorithm to solve the problem. And mind you, human. No computers yet. Human must solve the problem. Computers don't really solve anything by themselves. Now this next step, this is where programming comes in. Now the human, having solved and understood the problem, now feeds this algorithm into a computer program. He writes the computer program and thus instructs the computer in how to attain a solution faster. Then computer, now understanding human, right? Now they speak the same language because human learns the language of computers. That's exactly what we're doing in this class. So now computer is able to execute the same solution much faster than human. So again, it's worth emphasizing that human solves the problem, but computer can do it faster once the human instructs it. And then once the human has written the program to solve a particular problem, then human just keeps using the computer so that the problem can be solved faster. And it goes on and on. New problems are found and new programs are written. So let's take this step by step. It all begins with a problem. Right, so we said first step is problem is found and understood. So let's say, take this problem for example. We have a list here, a list of some elements that are numbers, integers, and the problem is this. Does this list contain the number 7? Right, it may seem trivial to you, and it obviously is, but imagine what if this list is a billion elements long. So with a human eye, it would be hard to tell, right? So the human here is scratching his head, and computer has no idea. He doesn't understand the problem, right? Well, neither does human at this point. Well, how do you go about saying that does it contain or not contain a particular number? Then all of a sudden, human comes up with this solution. Human says, well, I can take one number at a time, sample one number out of the list. So this is the algorithm that the human comes up with, and this is a typical algorithmic notation. These tabs mean that, so we're saying for each element in the list, and this is just plain English for now, we look at each element, and for each element, we compare it to the number 7. If the element is 7, then what this return true means, it means that we simply say that yes, the list contains the number 7. And then at the end of looking at every single number, if we didn't say that yes, it contains it, that means by default that it doesn't contain it. That's why here at the end we return false. That means we look at every element. If we see a 7, we say we see 7, it contains it, and we halt the algorithm. And if we are at the end of the list and we have not observed a 7, we say no, the list doesn't contain a 7. I hope this makes sense. This is a fairly easy algorithm. Now, why did I highlight these in red? As you see, the list does contain 2 number 7s, but I am not asking here count the number of the number 7s the list contains. The question is simply, does it contain a 7? That means that if you go one by one, once you reach the 7, you will simply say yes. And it would be a waste of time for you to complete the cycle and look at any more numbers. That's why you will never get to the 7, because it is irrelevant, right? You already see that the 7 is there. But unfortunately, computer still doesn't understand you. The computer says, I don't know, I don't understand any of this. This is English, I don't speak English, right? So step 3, this is where the algorithm comes in. Now the programmer, having solved the problem, writes a computer program and feeds it into the computer. And now all of a sudden computer says, okay, now I get you. Now I know how to do this, and guess what? I can do it 1,000,000,000 times faster than you. So from that point on, we go to step 4 and 5 and complete the cycle. So the human solves it and then writes the instructions for the computer. Now there are five separate generations, so-called generations of languages that are recognized today, 1GL through 5GL. And so here are some of the examples of computer programming languages that fall into different generations. So generation 1 is your basic ones and zeros. It's binary code. It's not human friendly. The second generation is a bit more advanced, but not really. These are your assembly languages such as x86, MIPS, and a bunch of others. So these are one step higher than binary. They do contain some words or whatnot, but still, if you ever look at one, unless you study assembly languages, they are not that easy to understand. Under the third generation, this is where we have C, C++, C#, Java, and many of the others. So these are called mid-level languages because they do contain some English words and reserved words and controls, but they are low enough that you really need to understand computer memory, how everything works on a low level. Otherwise, it is very easy to shoot yourself in the foot. Now, the boundary between the third and fourth generation is often blurry, and the fourth generation is said to be simply the advanced version of third generation languages. Python, which we're studying here, falls under the fourth generation, and you will see very shortly why. In addition, Ruby, Perl, SQL, and many others. So very often somebody would combine third and fourth generation because they are kind of the same, but there are many advanced nuances about 4GL that make it easier for humans to write computer programs. And finally, the fifth generation, which is extremely advanced, and that is very close to English. And this kind of programming language is what artificial intelligence research is all about. Some of it is OPS5, Mercury, and many others. So this is what's called a natural language programming, and it is incredibly advanced. So why are we studying Python as opposed to Java, C, you name it? Well, here's why. This is the same algorithm written in pseudocode that we saw a few slides ago. And believe it or not, to the right is the same thing in Python. Go ahead, you can compare the two, and it really is that simple. So some of the differences simply is here we say that the list gets these values. For each element in English, we simply drop the each, and it's 4 element in list. We replace the word equals with double equal signs, and we will learn all about that later on. And the rest is the same. So notice that when we put a colon, that means that we are going to be indenting with tabulation, and that means that everything. So these two statements are both under this loop here. And the same way, this statement, return true, is under this if statement. So whenever we say colon and then tabulate, that means we are indenting, and whatever comes after is under the parent level. And again, don't worry about any of this just yet. Everything will be clear later on. And if you're wondering, why is the language called Python? It has nothing to do with any kind of snake. It has to do with Monty Python's Flying Circus, which is a British comedy group. Now, this is absolutely crucial for you to understand. You will have major troubles in this course if you do not understand this, so please take the time to understand why this is. So there are 3 most important logical operators in any programming language. They are AND, OR, and NOT. And these are what are called truth tables. So the AND operator has this property. So we have here X variable, Y variable, and here is the result of X and Y. Similarly, X or Y, and the NOT operator takes only one variable, and X. So we have X and not X. So x and y here, they have the same inputs. X goes false, false, true, true. Y false, true, same here. So the AND operator returns true if and only if both x and y are true. In every other case, the AND operator returns false. The OR operator is the opposite. It returns false if and only if both variables are false, and it returns true in every other case. And the NOT operator simply flips the variable in question. So if the x is false, not x is logically true. And likewise, if x is true, not x is false. And here is a meaningless joke. So if you're speaking like in a programming language and somebody asks you, hey, do you want cake or ice cream? A programmer would say, yes, it's true. It's either or both. It's yes, please. It's a little bit different for humans. Again, a crucial point, that's why I put it in the first slide deck. Programming comments, they are a way for a programmer to communicate first with the same programmer at a later time. So you leave comments for yourself when you say look at your code a year or 10 years from now. And also you leave the comments for other programmers to understand what you're thinking and understand your thought process. They are completely ignored by Python interpreter or by any other interpreter or compiler. Programming comments are always ignored and have no impact on the execution of any program. Right? They are only for humans, and they are very important to include in your program so that both you and others can understand what it is you're trying to do. Always, always, always comment your code. If you're ever in doubt if you have enough comments or not, it's a no. Always over-comment if you have to. Leave a lot of comments. So here's an example. In Python, an inline comment is initiated by number sign. Anything following a number sign in a Python line will be ignored by the interpreter and not executed. So for example, this first line, it says, I am a comment, I will be ignored. This next line has no comment, it will be executed. So this guy says, I will be printed. And even though this is the same thing, this one is commented out, therefore it will not be executed. And here's again is a meme, as a joke. This programmer says, oh, I'm coding, I'm cool. And then, oh, I'm done, I'm saving time. And he remembers his instructor saying, always put enough comments. The programmer is laughing, I know what I'm doing, I don't need any comments, and opening the file sometime later, and all of a sudden the programmer sees hieroglyphics and doesn't know what is going on in the program. And of course, the programmer is mad. And again, always, I can't say it enough. Comment your code. And again, here's another joke. Some of the things programmers wonder, why is the program not working? Or sometimes, why is it working when it shouldn't be? It was working fine for me yesterday. I don't know what happened. And finally, even for your own programmers, who wrote this garbage?